Good afternoon. Welcome to the Fast Data Theatre. We are going to spend the next half an hour doing a quick comparison of options you have for choosing a data streaming platform. I'm not going to give any spoilers, but we're going to talk a little bit about why Kafka isn't the only game in town. Okay, we're going to start with a quick history of messaging and streaming. And I like to think about this in terms of four eras, sort of going back to the 90s. In the 90s, you had the messaging era, right? And this is where you had the big players, your IBM with their MQs, you had TIBCOs. They were very much doing messaging, lots of stuff with transactions, two-phase commits, that sort of stuff, very much point-to-point interactions. And you saw this in lots of banks, lots of technology companies, that sort of thing. Moving on into the 2000s, you had the JMS era. And if you remember the JMS era, we had these message-driven beans talking to your message-oriented middleware. And I hate the term middleware, but you've got things like WebSphere, WebLogic, JBoss. And JMS was all about the managing the interface between the message-driven beans and the middleware itself. It wasn't a broker protocol per se. Into the 2010s, you had AMQP, the AMQP era, and this is where we got technologies like ActiveMQ, Cupid, RabbitMQ, and some really great stuff. AMQP was a standards body. It came out of some of the banks and some of the tech companies, and really that was all much easier to connect different systems together. We then had sort of the big data boom, right? And the big data boom is still amongst us. We're here at Big Data London, right? The name is on the front door. Suddenly we've got data that's being generated at a size and scale that we'd never even thought of before. And if you were around at the time of the big data hype, you'd have heard of the three Vs, the volume, velocity, and variety. And then the marketing people got involved, and there was veracity and value. But really, we're talking here about data arriving at velocity that we couldn't have dreamt of before. Okay, so really now we've got data coming off the wire as at pretty much light speed, and we're at a position where either we're going to have to put that data into a warehouse and probably process it tomorrow. Well, it's probably no good tomorrow. This is fast data. That's what we're talking about. Or we need to be able to process it in real time, or we drop it on the floor. And so LinkedIn came along, and they gave us Apache Kafka, and this was around about 2011. And this is almost where the story stops, right? Kafka is an era-defining technology. There were some other things still kicking around. We've still got RabbitMQ. We've got Redis that's doing a little bit of streaming. There's Pulsar that comes along. That's based on Apache Bookkeeper. It's got this kind of separate storage and compute thing going on. And some of the cloud providers, you've got solutions for Kinesis and PubSub, but they're very much tied to their own ecosystems. Really, the era-defining technology is Kafka. And what we saw is a whole ecosystem of technologies built around Kafka and built around the Kafka API. We had Storm in the early days, then we had Spark, and Spark structured streaming. And I think Databricks are doing something with Project Lightspeed to improve structured streaming as we talk. You've got Flink, and then you've got the whole Kafka ecosystem as well. You've got Kafka Connect, you've got Kafka Streams, you've got KSQL, all built around Kafka as the dominant technology of the last 10, 11 years. And Kafka really was a game changer, right? It did things that simply we couldn't do before. It was built for cheap commodity hardware that you could scale out. Often it was kind of end-of-life hardware that was kind of on the heap, ready to go. You could just deploy these servers, deploy tens of them, hundreds of them, whatever you want to do. It had a really cool API and a meta model, and it kind of is the lingua franca for how we talk about streaming now. We talk about producers and consumers, and we talk about consumer groups and topics and partitions and brokers, and this is kind of how we talk when we talk about streaming now. And this ecosystem that I was talking about, like literally thousands of connectors and integrations, all with Kafka. It is, however, fairly complex. It's actually quite hard to use. It's quite hard to deploy. It doesn't make that good use of modern hardware, and Moore's law is still a thing, right? the number of transistors on a chip continues to go up. They say it's doubling every 2 years. If you go compare that back to 2011, the number of transistors on a chip has gone up 50 times, right? So we're seeing much denser CPUs in terms of cores. We're seeing much denser storage as well. SSDs are now the prevalent storage technology. NVMe even better than SSDs. And that change in underlying infrastructure is one that actually Kafka hasn't been able to take advantage of because it's built on Java with the Java virtual machine. And this is where Redpanda comes into play. And so I'm from Redpanda, and we're going to spend a little bit of time talking about Redpanda and how it compares with Kafka and how you can compare the two. So what is Redpanda? Redpanda is a brand new technology for streaming data. It is built on the Kafka API. There isn't a single line of Kafka code, but it's built on the Kafka API. So all of the meta model we were talking about earlier, all of the connectors, they all still work, right? The whole thing still stands up. But it is built in C++, which means it's much more aware of the hardware that it's running on, and you can do certain optimizations to really take advantage of this modern compute that we now have available to us. By being in C++, it uses this framework called C*, which comes from the ScyllaDB project. What that does is it actually runs pretty much a whole version of the software stack on every single core. So if you've got a 32-core box, we're almost, not quite, but almost running 32 Redpandas on that box. We don't then have the problem of sharing memory and sharing file descriptors and sharing anything between those cores. Every replica of every partition is pinned to a single core. So you get very consistent and predictable performance. You're not moving stuff around, and as you have with Kafka, where you're kind of running in the Java virtual machine, you're not really aware of what hardware, what cores you're on. It's all shared. So you get very predictable and very good performance, even under high load. It doesn't use the page cache, and the page cache was one of Kafka's great innovations. They said we're not going to put everything in the Java heap because then we've got to do garbage collection, and that's always tricky. So they used the page cache to get good optimization when reading from disk. Well, with Redpanda, because it's in C++, we've said actually the page cache doesn't really know much about streaming. It knows about writing data to and from disks. But we know when you're doing streaming that we're doing sequential I/O. We know that we're only reading forwards. We're not going backwards ever. So we can actually be very predictive about what we cache in memory and how we use that. So we're not using the page cache. We're using direct disk access, which again means we get much more predictable performance from what we're doing. Okay, so we're now going to spend a bit of time looking at Redpanda and Kafka side by side, and what it would take to run Redpanda in a production environment. We spent quite a bit of time comparing, and performance is important to us. It is one of the things that we talk about at every company meeting is performance, and particularly about throughput and latency. We use a number of different benchmarks, but one that we use quite a lot and that we're going to talk about here is the Open Messaging benchmark. Now, Open Messaging is a project. It's part of the Linux Foundation. It had some quite grand ideas of doing some reference architectures and specific bindings. Actually, probably its most famous export is the benchmark itself. But this is an open source benchmark that you can go and download, and you can run this, and you can replicate everything that we're going to talk about in the next 15 minutes or so. You can do that yourselves and get the results and see for yourself. It has integrations for, I think, 13 different messaging systems, JMS, Kafka, RabbitMQ, and various others. And we've got one for Redpanda as well. Actually, you can use the Kafka, and pretty much the Redpanda one is the Kafka, driver, but we've then got configurations for deploying Redpanda as part of that. For these tests, we've run 3 different workloads, a small, a medium, a large. The small is 50 megabytes per second, the medium is 500 megabytes a second, the large is 1 gigabyte per second. And we're going to run these on Amazon EC2 compute of differing sizes, and then we'll compare the results for what the performance looks like. All of these tests I've run with TLS and SASL authentication turned on. And the reason we've done that is because almost nobody is deploying Kafka or Redpanda without security turned on. Okay, we're putting audit information, or we're putting customer information, or we're putting financial transaction information through this. We can't have it with security turned off. That's simply not going to pass muster with the accreditation people. So in order to make these benchmarks fair and representative, I've run them with security turned on as well. And if you're comparing performance between systems, it's always a question that's worth asking is, have you got the security turned on? Okay, results. So this is the medium workload. This is the 500 megabytes per second. We're running this on i3 3x large, so this has got NVMe disks. The graph on the right is our end-to-end latency percentile graph. And we've got Redpanda in the red, and then we've got a couple of traces for Kafka. So Redpanda on 3 nodes is doing 17 milliseconds end-to-end latency at P99.99. Okay, 17 milliseconds. That's from the producer to the broker and back again to the consumer, end-to-end. The same test running Kafka on the same 3 nodes simply doesn't complete. It cannot run that workload. Okay, it can't sustain the produce throughput. It can't sustain the consume throughput either. With 4 nodes, that's the line in the gray. Kafka is completing, but we've got something like 389 millisecond latency at P99.99. With 9 nodes, we're still getting 113 millisecond latency. So tail latencies on Kafka 10 times higher with 3 times the hardware. Okay, and when I say that Redpanda is fast, we're in the fast data theater, that is what I mean. 10 times higher tail latencies, or 10 times faster, with 1/3 of the hardware. Okay. When we look at the average latency, the chart on the right, the Redpanda line is the red one, very consistent. And when I was saying about the architecture and the way it's written, we get really, really consistent latency. Kafka again, on the black and gray lines, you see this real variability. This is the average, and we're still seeing variability in the average from sort of every second or half second. This is to do with the way it's working with the page cache. It's to do with the way it's working with the Java virtual machine. Real variability, and you can see here, average latency on Kafka is still 2.5 times that of what we're seeing on Redpanda. On a 50 megabyte a second workload, this is a much smaller workload. Actually, the comparison is a little bit less stark. The reason for this is actually we're undersaturating the hardware at this point. It's quite a small workload for i3 X large, so we're actually struggling to really stress the architecture, so we don't see the benefits quite as much. We're still average latency 37% faster and 1.9 times faster at the tail, but a little bit less stark on this one. If we go to a gigabyte a second, again, with 3 nodes on a 3 node by 3 node comparison, Kafka can complete the workload. On what we've got here, we've got 6 nodes, and you can see the tail latencies are over 6 seconds, right? So that means you're waiting 6 seconds end to end. If you've got that, and you've got that connected to an app, and you've got that somewhere in a customer interaction, no customer's waiting 6 seconds, right? They're gone. They're on a different site, okay? You've lost that customer at that point. And this is happening at sort of P99.9, okay? So this is 1 in 100 or 1 in 1,000 customers, or 1 in 1,000 interactions that a customer might have. They might have 5 or 6 interactions in a given mouse click. It's coming back in over 6 seconds, right? That's not going to work. With 9 nodes, much more predictable, but we're still 7 times faster than Kafka on 9 nodes. Lots of variability in the average as well, particularly with the 6 node workload. Okay, so we've set the scene now in terms of how we size compared Redpanda versus Kafka. We're now going to talk a little bit about how many nodes that's going to actually translate. And when I think about the size of a cluster, and this is perhaps where Redpanda and Kafka could differ a little bit, we need to think about the nodes that we require for throughput. We've just looked at that. We also need to look at the number of nodes that we need for retention. And quite often retention can be the factor that really dominates how we size a Kafka cluster. Redpanda has a capability for tiered storage. This has this is quite a nice feature. What it does is, when you're writing data to Redpanda, as soon as the log segment is closed, it will asynchronously copy that off onto an S3 compatible object store. So that could be, well, it can be S3 itself, it can be on Google Cloud, it could be Sept, it could be our friends at Min.io, who are over there somewhere. That segment is then is copied over to there, but Redpanda keeps track of the offsets. If then, as a client, you come back and say, well, I need some data from yesterday, I want to read data from this offset, that's completely transparent. You don't need to go to a different endpoint or anything. Redpanda can say, oh, I know where that offset is, that's up in the cloud storage, I'll go and get that. It brings it back onto disk, and then starts serving the topic from that point. Even better, because we know that you always consume from Kafka Redpanda sequentially, we can go and get the next block and bring that one back, and therefore all your subsequent reads are going to be at line speed. So you pay a little bit of latency on the first read. Everything else as you read, as that slow consumer comes in, is reading very quickly. You can also then use this to have separate clusters for just read replicas. And we've got some customers that are using this where they're doing some KSQL workloads. They can keep their production cluster for kind of their live operational interactive type workloads, but anything that's got an analytic type, it might be going and doing a big read from somewhere, they can run that on a separate cluster. They can run that in a separate data center if they want to. It's still reading from that S3 storage. So when we then look at how many nodes we need, the nodes required for retention then becomes, we're then doing different calculations. There's a lot of numbers on this chart, but we'll focus on the bottom two rows. So this is our 1 gigabyte a second workload. If you want to have 1 day's worth of retention, you're writing at a gigabyte a second, that's going to be 260 terabytes worth of storage. So if you're doing that on Kafka, you're going to be looking at 18 nodes from the get-go. Remember we said we needed 9 nodes just to handle the throughput. We now need 18 nodes to handle the retention. With Redpanda, with tiered storage, we can just go with the 3 nodes that we needed just to handle the throughput, because we've got the other storage is then off into S3. So at this point, we've got 6 times savings in terms of the size of our production cluster. When we then look at the costs of that, there's 3 things we need to factor. Right, we need the cost of the brokers themselves. We need the cost of Zookeeper, and we'll come on to that. And we then need the cost of the S3. We still need to factor that in. So comparing like for like, again, a lot of numbers on this chart, but we'll go straight to the bottom rows. Kafka, we're looking at, when you're including the 18 brokers that we need, that's $35,000 a month just in brokers. You've got Zookeeper, which is another $400 a month. That's coming in at $432,000 a year. 4.6 times, almost 5 times the cost of running Redpanda in production for a 1 gigabyte a second workload. And that's the same for the smaller workloads as well. I think it's 4.6 on the 500 and 2 times on the 50. The real difference in cost. And I talked a little bit about Zookeeper. There's no Zookeeper in Redpanda. That's one of the things that is part of the core design principle. It's designed to be simple to use, it's designed to be simple to deploy, and it's designed to be reliable. So there is no JVM, as we've talked. There is no Zookeeper. Everything is written in Raft. The internal state of the cluster is managed in Raft. Every partition of every topic is a Raft consensus group. And this gives us very good performance, but it also gives us a much safer implementation. The Kafka ISR mechanism has been shown by independent testing to have flaws in it where you can lose data. And this is something that the original authors of Kafka have acknowledged and said that was a design decision they took. Well, the design decision that we took is that we shouldn't be losing your data. Like if you commit your data to us, we are not going to lose your data, right? That is super important, particularly if it's transaction information, particularly if it's audit information. That data can't be lost. So Raft gives us that, and it also means that we don't need to use Zookeeper, which is fantastic. It is all deployed in a single binary. There are no third-party tools. There are no external dependencies. If you're running the schema registry or if you're including the proxy, that's a single binary. It's also got automatic leader, disk, and partition balancing. So we don't need to have cruise control. We don't need to have any external components to keep the thing running. It will balance itself for you, unless you want to turn that off, which you can do. But it is therefore much easier to use. It's much simpler to manage. It's also got built-in Prometheus and Grafana integration. So again, you don't need third-party tooling to monitor this. This is all out of the box. It is a cloud-native solution. We've said, I think already, it is wire compatible with Kafka. We've got a smaller footprint, and we've got the tiered storage. So it is a unified experience. So coming back to our pricing, we're looking at total cost of ownership. So 4 things we need to think about. First is the prime cluster cost. We've looked at that already. We need to look if we're using a DR site of any data transfer costs. Never underestimate data transfer. We need to look at disaster recovery infrastructure, and we need to look at administration. Laying all that together, again, we can focus on the 1 gigabyte per second workload on here. Total cost for running Redpanda at that high throughput for 1 year, $187,000. Okay, this is in EC2 in Amazon. The same for Apache Kafka, $1.2 million. We're talking about a 7 times cost reduction. Okay, and this is, we've talked about it being fast. We've talked about it being cost effective, and that is really what Redpanda is built upon. We have a handful of different deployment options that I'll run through for you. First of all, it is completely free to use if you want to run the source available version. So you can go and you can get started with this today. You can deploy it on 100 nodes, 1,000 nodes if you've got that much data, but I'd be quite impressed if you needed to. You can use that completely free without any restrictions, unless you are planning to sell it as a cloud service, which hopefully none of you want to do. But yeah, you can use that for your own purposes as much as you like. The enterprise features are licensable. So if you need the tier storage, we license for that on a per core basis. If you need Redpanda console, that's also licensable. But we give you 24/7 support as well as part of that. We then have a handful of options for deploying in the cloud. We have a Kubernetes Operator. So you can deploy your operator, you can then spin up as many Redpanda clusters as you like. That will run on it's standards compliant Kubernetes, so you can run that in pretty much any Kubernetes that you can think of. We also have a Helm Chart as well. So if you don't want to go the operator route, you can use the Helm Chart. You can configure the hell out of that and deploy it the way you want. That is available. That's free to use as well, or you can use that supported from us. We've then got 2 managed cloud options. First is bring your own cloud. This is where we run a control plane. You have the data plane in your cloud environment, and we then have an agent that will talk back to the control plane. You can then spin up clusters from our UI. You can create topics and do that. It's then running in Kubernetes in your cloud environment. Or we have a fully managed offering where you come to us and you say, I'd like a cluster, and we give you an endpoint, and you don't care whether it's running on whatever. You can control what region it's in, you can control what cloud it's in, but how it works, that's for us to worry about. We will manage it, we will monitor it, we will do any fault finding or troubleshooting, and we'll let you know when you're having problems. If you're running out of space for some reason, we can just ping you and say, hey, you need to adjust your attention on this. So we will completely manage that for you. That is it. Happy to talk more if you want to come over. We're at booth 462, which is kind of all the way over that direction. We've got free T-shirts. There's also a free ebook, which you need to scan a QR code. We've got a Slack community. We'd love to talk to you in there. The quick start, we've got Docker images. You can be up and running pretty much before you get to the front of the lunch queue if you want to get that going on your laptop or your MacBook. Very simple to use, as I said. Ready to go. My name is Tristan Stevens. My QR code's in the top corner. Happy to talk to anybody, but come visit us at the booth. Really nice to see you all. Thank you very much.